Thanks everybody for joining us today. Just a few brief remarks. Will be a question and answer format, so you'll be able to ask questions throughout if you want, and there will be time at the end too, for further discussion. And we will be mailing a completion certificate for your CPD for afterwards. Plus, we will be recording. So if you know of anyone who was unable to attend, we're happy to send the link out as well. And also expect a short survey. And please take the time to fill that out. So let's get going here. Just a brief introduction to Craig Stoll, the Landmark team lead for process engineering and our subject matter expert for process safety valves. Craig brings over 30 years experience in facility design, process optimization, construction management. He supported gas plants, oil facilities, petrochemical operations, pipeline systems across Canada, US, and internationally. Expertise includes mechanical and process design, debottlenecking, HAZOP, risk assessment, incident investigations, regulatory approvals, and interdisciplinary project executions. Just a little bit of background. He's worked in nitric acid petrochemical plants, led PSV replacement programs, de-superheater upgrades, construction support, and petrochemical operations in Alberta and BC, oil and gas facilities, facilitated what-if reviews, process engineering for battery expansions, sour gas and water injection projects, served as lead engineer, including vapor recovery systems, energy transition pipeline support, and olefin blending systems, and facilitated process hazard analysis. This deep expertise, pressure relief design, overpressure risk assessments, PSV sizing, and compliance with ASME, API, and regulatory requirements. I think you can tell Craig's exceptionally well suited to lead our session on pressure safety valves. With that, Craig, over to you.
Thanks, Mitch. That's a long list, but I guess it just shows how old I am. So yeah, thanks, Mitch. So yeah, thanks everyone for coming. Good afternoon. This seminar today, it'll be about 45 minutes. If you have questions as we go along, feel free to put them in the chat, and I'm not monitoring that, but Mitch is, so maybe we can answer them as we go along. But our goal today is to just have a basic overview of pressure safety valves, what they are, some of the regulation codes and standards, common types of PSVs we encounter in the industry, and the main part of it will be going over credible causes of overpressure, and trying to make it practical for all of us. So, and a few other considerations that we'll get into. So moving right along, yeah, what is a pressure safety valve? Well, I'm sure if you're here, you might know already, but essentially it is to protect life and property by venting process fluid from overpressuring a vessel, equipment, or piping system. It's often the last line of protection in a system when all our alarms and shutdowns may have failed. The PSV might be our last line of protection from sometimes blowing stuff up. So they're very important. So what we're covering today are PSVs that are set at 15 PSI or higher. They open at a set pressure and reclose when the system pressure drops below the set pressure. What we're not covering today are rupture discs, tank relief, safety valves, and vacuum protection. So it's just, I like to talk about a little side note about acronyms, because there's a lot of acronyms for a PSV. You might see PRD, PRV, which one is right? I'd say generally for Landmark and most of our clients, PSV is used most of the time. But we also see temperature relief valves, TRV, pressure relief device, PRD, and pressure relief valve or pop valves. So caution with PRV and mixing PSV and PRVs on PNIDs. Forgive all the acronyms here, but yeah, typically we use PSV or TRV, where a pressure PRV is a pressure regulating valve, which is generally used to drop pressure in a system. You can see the diagram on the right here where we're dropping through regulators. So yeah, sometimes you got to keep your just keep your acronyms correct. And so we are talking about PSVs, and I'll refer to them as such throughout this presentation. Some of the design standards that are really important when we're considering PSVs are API 520. This has equations and sizing for liquid, vapor, and multi-phase fluids. It also has many considerations for the installation of PSVs, talks about inlet and outlet pressure losses from your PSV. So really important. We go to this a lot. API standard 521. This aids in the selection and helps guide your decision to discover overpressure scenarios, and helps you not only prompt for all the overpressure scenarios we might encounter, but has equations and guidelines to help determine relieving rates. API 526 is more like the dimensional guidelines for construction of valves, and also defines API orifice areas. 527 covers pressure testing standards and such for all the conventional bellows and pilot operated valves. And if we're dealing with any vessels in the system or boilers, then ASME section 1 or 8 might come into play. We also might have local rules and regulations that we have to consider, both national and provincial. In Alberta, we might deal with CSA, B50, B51 or 662, AR directives, and ABSA regulations. And if you really want to get into like the nitty-gritty of PSVs and design, these industry handbooks are invaluable, like the Emerson Pressure Relief Handbook and Crosby. They're quite similar, and yeah, there's a lot of detail in each of those handbooks that, yeah, if you, like I say, if you really want to geek out on PSVs, that's the place to go. So what are the common types we encounter? We encounter conventional spring-operated PSVs, balanced bellows, and I'll get into the details of each of these as we go, and pilot-operated. So those are generally the most common that we deal with. Conventional spring-operated basically have a spring that's set at a set pressure, and when the process pressure exceeds the set pressure, the disc opens and lets fluid out, and it resets once the process pressure drops below the set pressure. One of the limitations of a conventional PSV is on the outlet side, you're limited to 10% of the set pressure. So sometimes that can be a problem in existing systems where you have constraints already or other things that we'll get into. Balanced bellows, very similar to the spring operated, but it has a bellows to minimize the effect of back pressure. Yeah, so generally you can live with about a 30% back pressure on a balanced bellow, sometimes more, depends on the vendor. And The one thing to note with the bellows is you have to vent process fluid to like out of the bellows. So if it's toxic, like it's got H2S or something like that, it's something to be considered where that's going to go. If it has to go into a flare system, or maybe it's ammonia that has to be vented outside a building away from people. So it's one of the kind of quirks of the balanced bellows you have to keep in mind. Pilot operated PSVs, they don't have a spring, they use a pilot system. Generally, as the operating pressure gets closer to the set pressure, you get a better seal. And I'll get into the balanced bellows and the spring operated have issues when you get too close to the set pressure. And you can also have very high back pressures in a pilot operated PSV, as high as 98% in some manufacturers' PSVs. So this is a bit of a comparison table. A lot of what we've talked about, it's just summarized here, like the back pressure limits. Sometimes a conventional, like this diagram from the Emerson handbook on the right, shows the difference between a conventional operated versus a pilot. Like, so as you get bigger in size, just the sheer amount of steel you need in that conventional PSV starts pushing its price higher than the pilot operated PSV. So sometimes there's a balance there. Yeah, the pilot can be susceptible to fouling or freezing, so that's something to consider too. If it's a really dirty fluid, you might have to have filters on your pilot system. So those are the three types of PSVs we generally deal with the most. Yeah, specifying the fluid is important when you're ordering a PSV, because they both have different, like the vapor, like it says here, due to its expansive energy, can use generally a flatter trim, where a liquid trim needs to have some modified geometry to help it open. And generally a liquid trim can be used in vapor, but not vice versa. So keep that in mind. Like ideally you get the trim suited for your liquid, but you know, sometimes you're dealing with existing equipment, and yeah, sometimes you have previous constraints. So I talked about earlier how one of the advantages of the pilot operated PSV is you can operate very close to your set pressure. And with bellows and spring operated conventional PSVs, we have this phenomena called simmer. So if we follow on the y-axis, we have the percent the valve has lifted, essentially, like from fully open to not open. And on the x-axis, we have the percent of set pressure. So as we approach that 100, like the set pressure, the valve actually starts simmering. And you can see the definition from Emerson here. It's basically that valve can't fully seal, and it starts to burp fluid and simmer fluid out. And then upon reseat, you can see, so as the process pressure rises in either one, you get to 100% open, and then as it drops, you need to drop well below the set pressure before that valve fully closes.
Excuse me, Craig, is that we have a question?
Yeah.
For two-phase flow relief, what trim should be selected?
Usually it's the liquid trim. Liquid trim is usually typical. Sorry, I didn't mention that bullet point there. Does that answer that person's question?
Yes.
Okay, great. So yeah, this is something to be aware of, and oftentimes like pressure shutdowns in plants are set at, no more than 85 to 95% of the maximum allowable pressure to keep your operating pressures so we're not like simmering PSVs. And it can lead to damage, like your PSV could chatter a lot and get damaged. So something to be aware of. So now after we've talked about the types of PSVs, how do we know when a PSV is required and how big it needs to be? So generally this requires a methodical approach where we examine the principal causes of overpressure for our system. That includes defining the boundary conditions, as well as the process conditions and the set pressure that we need, and then identifying credible causes of overpressure, determining the relieving rates of each of those credible causes of overpressure, and then calculating the minimum orifice area required for each credible cause. And then once you've done that, you can figure out what size of PSV you need. So sometimes one PSV is covering several causes of overpressure, which we'll get into now. So in terms of defining the boundary conditions, on the right, we've got a simple, pretty typical wellhead example. Wellhead's operating at 40,000 kPa. It drops from F class down to C class, like 600 ANSI, into a separator. So defining the boundary conditions, the things we should be looking for are spec breaks, vessels, control valves, outlet valves that can close a system, heat exchangers, pumps. Those are all areas where you might need a PSV. So in this wellhead example, we have a spec break at this control valve going from F to C, and then we have a vessel and we have valves that could close that system. So that's a boundary condition for that system. Defining the process conditions, well, we need to know what kind of fluid we're relieving, normal versus maximum pressures, temperatures, flow rates, all of your vessel and piping, like the maximum allowable working pressures and such, will generally define your set pressure. And if any control valves are in the system, control valve details. So identifying the causes, credible causes of overpressure. This is where I had mentioned previously API 521, section 4.4. It lists about 16. I don't expect you guys to read this whole table from API, but it lists a whole bunch of different causes of overpressure that we should be considering. The ones that we generally see the most are closed outlets, failure of automatic controls, control valves failing to control, internal explosions, maybe not as much, but transient pressure surges like water hammer, hydraulic expansion, and we'll get into each of these, and fire. Those are some of the most common ones we see and deal with. But as you can see, in our typical oil and gas petrochemical industry, there's a lot of different ways we can see overpressure scenarios. So what can an inadvertent closure of an outlet valve expose that equipment to overpressure? So on the right, you can see a pump, a couple pumps in parallel, and there's outlet valves, MOVs, that could potentially close. Maybe there's a manual valve that could be inadvertently closed. So, pumps, compressors are all good places to look at that. Any downstream, spec breaks across the control valve, or heat exchangers, especially on the demand side. So in this diagram here, if we had a line heater, say we're heating up oil going through this line heater, we're adding heat, and someone accidentally closed this valve, we could easily overpressure by heating up that fluid. So that's another scenario of closed outlet that could cause overpressure. Failure of automatic controls was the next one, and common spots we want to look out for here are pressure regulating valves, PRVs, pressure control valves, and while not exactly a failure of an automatic control, manual bypasses around regulators or control valves can sometimes flow more than the control valve itself. So those are something to be really aware of if someone cracked a bypass around a control valve. Like I say, they can often flow a lot more than the control valve. Pressure transients, water hammer. This is kind of like, yeah, a train hitting a wall. Closing valves at the end of liquid pipelines can cause transients. The longer it's a momentum thing, so the more mass and the higher velocity you have in the pipe system means the more you can raise that system pressure, and you can easily double, triple, or even more times the MOP of a pipeline if you're not aware of water hammer. And the interesting thing with water hammer is it cannot typically be mitigated by most like a conventional or pilot operated PSV typically, because they just can't react fast enough. So a couple ways we can mitigate for water hammer. The easiest, probably most common way is just to control valve closing time. If you're at the end of a big pipeline and there's ESDs, we just slow the closing time so that those pressure transients stay within the pressure rating of the pipeline. When you can't do that, or say like this water hammer could also happen at the suction end of a pump or suction of a pump if the pump just shut down hard and the flow into it stopped. So that's another way water hammer could happen. So sometimes you can't control water hammer with valve closing time, so you can get into these surge relief valve systems. The one on the right here is a Danflow surge relief valve system, which has super fast reacting control valves and like dampening vessels, surge vessels that help you control water hammer. So yeah, those can get interesting. Thermal expansion, we kind of talked about that in the case of that line heater where we're heating up like locked in liquid. So anytime we have liquid that could be blocked in outside or inside, like if you don't need a lot of heat to create really big pressure changes in pipe. So there's a couple examples here, or a few examples. If we just took water at 1,000 kPa and 5 degrees and heated up to 10.7 degrees Celsius or so, you'll hit 9930. So, it's a 6-degree temperature difference can really drastically increase a blocked in fluid. Southern Lights diluent.
Excuse me, Craig, we have another
Yeah,
question.
go ahead.
What kind of PSVs are used to prefer in water hammer in section 4.4 that you mentioned?
Well, typically we can't use PSVs to mitigate water hammer. So we have to, slow down valve closing times or use surge relief valves and dampener vessels. So yeah, I'm pretty sure, yeah. Does that answer the question?
I will say yes, move
Okay.
forward.
Okay. We can maybe talk about it later after.
Sure.
Yeah, so Southern Lights diluent, getting back to hydraulic expansion. Yeah, like this diluent is a little more squishy, I guess you'd call it, than water, and takes a little more temperature to get you up to 9930. And then something like ethylene, this is like ethylene in a supercritical phase. It's even more squishy, but still it doesn't take, like, all of these temperature differentials could easily be seen in a, if you closed a system in the morning and it heated up on a summer day, like, these kind of temperature differentials are not unheard of. So TRVs are typically used to basically burp fluid out as yeah, the fluid expands. Hydraulic expansion, yeah, another way this can happen again is if you're heating up, say, some kind of fluid, we've got our heat medium going through this heat exchanger and we're trying to heat something up and we close this, that could easily be a cause of overpressure. So heat exchangers, keep an eye out for. Fires, typically we size for pool fires. So this comes from a pool of flammable liquid accumulated under vessels. Piping is usually not considered a credible source of overpressure in a fire. That's according to API 521. And yeah, basically the bigger the vessel, because the equations are based on the surface area of the wetted area. So if your vessel's half full, that bottom area, so the bigger the vessel, the bigger the PSV will be. And yeah, although there are equations for vapor-filled vessels to size a PSV, if you're heating that vessel enough up to to cause the vapor to expand, you're generally at a temperature where the vessel has become so weak. It's just this sort of awkward thing. You're putting a PSV on the vessel, but the vessel might fail because the temperature has gotten so high by that time. So yeah, sometimes it's hard to put a vessel in without a PSV due to the ASME codes. So anyway, there are equations for that. Another common thing we see awkwardly is check valves defining a spec break, like this system here where we've got a 600 ANSI line going this way and we're trying to tie a 300 ANSI system in. Check valve failure is practically guaranteed. You can't not rely on them for overpressure protection. So if you only have one PSV in play here, or check valve in play, that PSV is going to have to be pretty big. API,
Craig,
yeah.
sorry, another question here. When piping is not covered as OPP case, according to API, what happens, suppose, across country pipelines for LPG or a high BP liquid and there is fire?
Like if the line was above ground or something like that. Because usually a line would be buried if it was a long pipeline. But I can answer the question. We had a system where we had a butane line. I'll just go back to the fire slide. We had a butane bullets that were feeding another plant, maybe 500 meters away, and it was an above ground 4-inch line across this field. And the question was raised in a hazard analysis: what if there was a grass fire? Would we, yeah, like, would we want a PSV on that? So we did do a calculation for that. So Yeah, I guess with anything, it depends. Like if you want to include piping, like there's nothing saying you can't, but API does say it's not a credible source of overpressure typically. Because your surface areas could be quite small. Hopefully that answered that question.
Yeah, I think we're good.
Okay,
Yeah.
thanks. Um, so yeah, back to sort of like check valve or misdirected flow. One of the strategies in a scenario that API offers up is to use double check valves of different types. And you could basically assume that instead of the full flow coming back and hitting that PSV, only one valve fails and the other leaks by 10% or something to that effect. So the PSV size that you would need, you wouldn't eliminate the need for that PSV necessarily with two check valves, but it could be a lot smaller. If you wanted to eliminate the need of that PSV, other protection, another layer of protection would be needed there. So now that we've gone over some of the sort of more common treadable scenario or overpressure scenarios, we'll just go back to this wellhead example. Well, and we'll just go quickly through some of the credible scenarios of overpressure. Say if this valve closed, we still had all the flow coming in, we have potential for blocked outlet being a credible case of overpressure. If this pressure control valve, excuse me, failed to control pressure or choke valve washed out, which is pretty common if you
Hey,
have
Craig, I have a couple more questions.
okay.
Did you mean two dissimilar check valves?
I think could be considered, yeah, different types.
Okay. And then another question, do you know if there's any justification provided for why check valves need to be different valves
That's just
rather
comes
than
from,
same design but with redundancy?
yeah, I think that's just the way it's worded in API. I'd have to like dig it up just to remind myself the wording, but I believe they specifically say, yeah, different types. But I think if you're getting into the like the debate whether two dissimilar ones have different failure rates, that's kind of becomes a hazard analysis type of question. So API, take it as a guideline, but it's not written in stone. I think if you have engineering justification to use the same valves and you had enough, backup to satisfy yourself, you might be able to do that.
Thanks, Craig.
Yeah, you're welcome. Good questions. Um, so in this case, getting back to our simple wellhead example, we've got blocked outlet, we've got a control valve that could fail to control pressure. Choke valve failure is specifically addressed in API 521 and talking about how it's quite common. And pool fire because we've got this vessel. So once we've identified these credible case of overpressure, well, we generally do an API 521 checklist where we've got all those scenarios and we can just, do our due diligence, kind of like identify that we've considered all these other scenarios and then our basis. And then you can see here, each of these cases requires a different rate. Like the blocked flow was 2 million a day. The wellhead choke valve failure could flow almost 7 times that blocked flow rate. And the pool fire was the smallest scenario. So essentially the one that requires the biggest area becomes our governing case. And in this case, it was choke valve failure. And often this could be like, depending how complicated your system is, this could be a bit iterative. Like the first pass, we might, identify all the credible scenarios that we have found, and then you review it with, operators and that, and you might get different ideas, like, oh no, this scenario doesn't apply because of this, that, or that. So in this scenario, you can see that so the orifice area that we required is 0.301 inch squared. And I'll just get over here. So once you've found your governing case, you need to define the orifice area that you need, or the orifice designation. And they come in API and ASME orifices. The table on the right shows that the ASME orifices are generally bigger. So in the case of our wellhead separator PSV, we needed a 0.301 inch or square inches orifice. So if we look at this table, well, we're in the F. So we need the area available on our PSV to be bigger than the area we require. So in this case, sometimes it's a case of like you don't want to pick an orifice that's too big, but you don't want it too small either. So in this case, we're really close, like we're within 98%, or like we're almost using the full area of a API PSV, where if we spec'd out an ASME orifice, we'd have like 16% extra area available. So if you size your PSV too big, like maybe say, oh well, why don't I just put in a G? Well, usually you don't want to spend more money than you have to, so the bigger orifice might bump you up into a bigger size PSV. And sometimes chattering can occur if your PSV is way too big. It could lead to chattering, rapid opening and closing, instability, and cause premature wear. So like I say, it's a bit of a not too big and not too small. In this case, I would probably opt for this one because 98% is maybe pushing it a little too close for my liking. Yeah, and here, this is a less typical example. This job was for a client at a petrochemical plant. We're replacing a 40-year-old PSV in quite an involved system. There was no information available on what that PSV was sized for, its basis or anything. Like it was installed back in around mid 70s or so. So essentially we had to do an analysis, and we found 19 credible causes of overpressure, which was at the time we asked ourselves, like, maybe this PSV is being asked to do too many things. And there was during the project it was decided that PSV was going to stay there, but we just need to size it for all these scenarios. And that one, this API checklist came in really handy because there's just so much to keep track of, and some of the cases were vapor relief and some were liquid relief, and yeah, it was a really interesting project. Yeah, and then the other considerations once you've figured out what size your PSV is going to be is ensuring that your inlet losses, so wherever, typically, like here's a filter where we've tied in to protect this filter, the inlet loss, so the pressure loss when that PSV is going from from the vessel to the PSV has to be less than 3% of the set pressure. So yeah, and generally you want to keep your inlet piping bigger, or sorry, as big as, or in this case we had a 2-inch going into a 1-inch PSV. But those hydraulics are important to check. That having too high inlet pressure can cause chattering and such, and premature wear to your PSV. And then on the outlet side of the PSV, we want to do hydraulics and ensure that for conventional PSVs, yeah, you're less than 10% of the set pressure at the back pressure when that PSV opens. And yeah, sometimes that's, yeah, PSVs going to atmosphere, it's easy, and sometimes you have a big flare system and it gets a little more interesting. Yeah, and that kind of brings us to the end, and can open it up for questions if there is any more.
Sure, is that I have a couple in the chat, Greg.
Just open that up here.
I don't know if you can, that you would like to answer probably, oh, it was previous person, is that is there any specific clause in API 521 for surge pressure that we can take credit the fast closure of check valve to alleviate the maximum surge pressure, or we can't?
Fast closure of the check valve for water hammer. Not sure I understand the question. Well, yeah, maybe if that person could
Yeah, is it
restate your question.
we'll follow up afterwards.
Okay.
Uh,
I see one from Blake. Hey Blake, what are the most common mistakes you see? Yeah, that's a good question. I would say like not even less experience, but just, you know, we can all make them. I think the biggest mistake is assuming, like I'll just go back to the wellhead example. I like to have pictures, just a diagram. Like often, like in this example, just assuming you know what the credible case is already. Like, oh, it's a wellhead separator. It seemed to be block flow is always the scenario we sized the PSV, or was the basis. So I think when you think it's obvious, that's probably when you want to pay the most attention and like be like, oh, am I really thinking of everything? Because if you think it's blocked outlet, oh, it's fine, it's blocked outlet. Maybe you're missing stuff. So that's kind of why we developed that API checklist, just so we keep ourselves honest and like go through like, yeah, yeah, or like, no, no, no. So yeah, we found that a really valuable tool that, so if someone's checking your work, they can come back and say, well, did you consider failure of automatic controls, for instance? And if they've checked that off this list as no, like not credible, then yeah. So I'd say the list is being pretty valuable for us in not overlooking. Yeah, say just be careful when you think it's obvious.
a question from Janine.
Yeah.
What is the difference between ASME and the API orifices? Is it mainly sizing or other design differences?
Well, their areas are different, essentially. Oops. So the ASME, let's go back to that chart. Sorry, just find my way here. Yeah, so this is like the area of those orifices, so the ASME are bigger areas, so they can essentially let out more flow. That's the main difference.
Have another question from Theo. Any thoughts on how best to manage address PSV discharge lines, low points, best to avoid, but not always possible to avoid?
Yeah, yeah, best to avoid for sure. Sometimes you like if it just so are you talking about if I had a like a PSV down here and you could have like liquid accumulating, say at the bottom there? If that's what we're talking about, then yeah, you might need a low point drain here that needs to be drained. If it could freeze, you probably want to make sure it's traced, and this is a really bad drawing, but yeah, you'd want to make sure it's traced so that it can't freeze. Uh, yeah, best to be avoided. You want to go up so that no liquid can accumulate upstream of your PSV, but I know it's not always possible.
Yeah, just further that. So yes, low point piping due to this design restriction.
Hmm. Yeah, if it's yeah, it's awkward for sure, especially if it's a gas line that could have liquid down there. I see the question. Yes, that's what I mean. The closing time is fast enough. Like, yeah, I'm not sure you can take a check valve credit for pressure transients. I've never had to do that myself, so I probably want to look into that a little more. That's a good question. Yeah, Quentin, he's one of our process engineers here at Landmark. To the question of this low point drain, if that could fill up with liquid, like if there's no avoiding that, you'd want to consider that in your inlet uh, pressure loss calculations. Yeah, I think,
Any other questions? All right, is that I think this brings us to the end. If you do think of any other questions, please reach out to Craig direct. I know he would definitely be able to assist and follow up and give you guidance on that front. And with that, as it has mentioned, we will send out your certificate for you. And that and please thank you everyone for coming. And please take the time to fill out their survey. So is it have a great day, everyone, and thanks again.
yeah, thanks everyone.